We're talking about exponential functions today, and it is review. We're going to, like I said, we're going to just kind of chat about some things, hopefully remember some of the stuff from grade 11 that you did. We're going to do a little bit of graphing today, and it's a bit messy. Graphing parabolas is awesome because there's 7 points that fit on the base graph, and then even with a good stretch, you can usually fit 5 of them and get a good sense of what the function looks like. But if you remember from grade 11, exponential functions and like reciprocal functions, not so much. It's harder to find those points. It's messier. Some of them are fractions decimal so fast that once you have a stretch, the points are gone off the grid really quickly. So it's a little bit harder. So we're going to be kind of doing a mixture of accurate graphing / sketching, where really what you want to get out of today is a couple of the important properties of these functions, how they're impacted by transformations, that kind of thing. And there's just a couple of key properties about these functions that we're really going to focus on. So make sure you come away today with that understanding, okay? But the other thing we're going to think about is, and that I'm a big fan of, is always thinking about the actual function that you're talking about, which is the input and the output. So if it's y equals 2 to the x, and my input is 0, 2 to the 0, what's my output? 1. Anything to the 0 is 1, except for 0. What about 2 to the 1? So this is just a little bit of review of exponents, because this is supposed to be the easy part, but some people maybe are like not fully confident in knowing what this is. It's supposed to be easy. Is it? 2. 2 squared is 4. And this is kind of interesting because these, like this exponential graph in particular, 2 to the x, is very similar to parabolas, right? And some of these points are identical. The curves don't line up, but some of the points are identical. And then 2 to the 3 is 8, whereas 3 squared, if you're doing a parabola, would be 9. And then 2 to the 4 is 16. And 4 squared is also 16, so the same again. And then after that, they become different, and the exponential graph starts to grow really, really, really fast, right? And so on and so forth. So you can continue to do those. What about 2 to the negative 1? This will come up a little bit later, but what's that? Very good. It's not negative 2. It's not negative 1. It's not anything like that. Remember, negative exponents flip things. So that's going to be something important to remember as well. Negative exponents flip the base of the power. Okay? So input and output. And just thinking about my input is how much I'm going over on the graph from some value, some anchor value. And then output is how much you're going up. Okay? What happens when the base changes? So this is interesting to me. Because it's not a transformation. We're going to talk about transformations today, but this is not a transformation. This is a change of function. These are different functions. You change the base, you change the function. But they're all related. They're all exponential. So we consider them all the same. But all of a sudden, my inputs are the same, but my outputs are different for the base function. 3 to the x does not follow this same pattern. It's related, but it's not the same. But they share similar properties. So we do talk about them all the same. But just remember, when you change the base, now we're mostly going to work with the base of 2 today. But when you change the base, you're actually changing the function. It's not necessarily a transformation. Don't think of it that way. Yeah?
Well, like, isn't, I guess not necessarily transformation. Is it just like a stretch?
It's similar in some ways, you're right. But it's not a vertical stretch. It's changing the function. Okay. What we're going to do when we talk about transformations, this is if the base is 2. This is if the base is like anything, like B. What does the A do? What does the C do? And what does the D do? And they do the same things as they do in other graphs. And yes, you could have a K value as well, but we're not going to worry about that because that makes it even messier. So what is the A value? We're going to write this down later. You can write down now if you want. What does the A do? Vertical stretch or compression, and if it was negative, it would, yeah, it would flip. It would reflect. Good. And the x-axis. What does the C do? Horizontal shift. So left or right. And the D is a vertical shift up or down. Again, we're going to maybe write this down. I don't know that you have to write this down. You probably know this by now, but the general transformations. But what I want, again, to point out is a big part of this, when you get a new function, is thinking about how does each variable change. If I change A or C or D, what properties of the graph does it change? And how does it change those properties of the graph? And then how can I use those properties, I suppose, to paint a picture of what the graph looks like and maybe sketch it or maybe graph it or whatever you have to do, right? This is the idea. And trig curves are a great example of that, because we can specifically say the A value changes the amplitude and the D value changes the zero line. Those are properties of those graphs. Can we do the same thing for a graph like this? So before we get to that, here's a question for you. What are the important properties of graphs? Can you give me one? Y-intercept. Any others? Tyler? X-intercepts, good, yeah. So the X and Y-intercepts, all the intercepts, good. Any more? Asymptotes. Some graphs have them, some don't. Does this graph have an asymptote? There's something to think about.
Like any transformations?
So transformations are a bit of a tricky one, because to me, transformations are what cause the properties to change. But you're right, especially in grade 10, we kind of talk about them as properties of graphs. So I think brainstorming session, that's good. Let's write them down. Transformations. But those are sort of what causes the properties to change. And behaviors, I like that one. Definitely. And there's other ones that are related to end behaviors. What else? Good. Good. Domain and range. Remember, domain and range, different functions have different domains and different ranges, and that's one of the ways we talk about how they're different. We compare or contrast them. So you might talk about the range of a degree 3 function compared to the range of a degree 4 function. And we know that odd degrees are different from even degrees in how they look, and that's again related to like end behavior. Right? So some of this stuff is overlaps, or it's the same, or it's similar, but different ways that we talk about properties of graphs, so we can compare them, how they're similar to some and different from others. Again, the type of function will dictate, like you mean like if it's a quadratic or that kind of thing, will dictate what the properties are. But I mean, you could think of that as certain. Good, positive and negative intervals. What else? There's a couple more, I think. Sure. Turning points, yeah. A hole. Certainly a property of a graph. Do you remember doing even and odd? Some functions are even, some are odd, many are neither. That has to do with symmetry. Apparently we don't remember that. That's okay. I think this morning they said degree of a function, which if you're talking about polynomial functions, again, is sort of a broader thing, type of function, kind of like exponential functions, but you can do the same thing. Yeah, Bradley. Yeah, amplitude. So then, good. We could write down all of the all of the properties of the periodic ones, right? But maybe we won't right now. But the period and the phase shift and stuff, which is kind of like the transformations as well. But anyway, okay, good. That's a pretty good list. Well done. Let's move on. Again, you can write this down or not. It's just something that we definitely need to know. And what this is saying is, for the exponential function y equals b to the x, if b is greater than 1, so for example, 2, 3, 10 to the x, 1.1 to the x is still greater than 1, so fractions would be fine. 3 over 2 to the x. Sometimes people say, oops, not to the 2, to the x. Sometimes people say numbers that are less than 1 are fractions, but not always, right? Not all fractions. Anyway, when that's the case, the graph looks something like this. This is something you definitely need to know. How would you describe this graph? What's unique about this graph that I suppose is different from the other one? It's increasing. Nice language, nice use of language. Always, everywhere?
Yeah.
Good, yep. This is increasing forever, at least on its domain. But its domain is everything. The domain of all of these is always everything, right? X is an element of the real numbers. That would be the domain of every exponential graph when you think about it. So, yep, increasing for everywhere. Where is the asymptote, do you know? Good, so increasing asymptote at y equals 0. These are some of the kind of properties. If it has no transformations, does anybody know what the y-intercept would be? 1, because anything to the 0 will be 1. It doesn't matter what the base is. 2 to the 0 is 1, 3 to the 0 is 1, 4 to the 0 is 1, 10 to the 0 is 1, good. But if it has transformations, that will change. Sure. Oh, we'll talk about that. You mean the next one? Okay. Let's get to that. So I think that's good for the first one. If you are less than 1 but greater than 0, so in other words, less than 1 but positive, how does the graph look different? There's some examples. 0.1 to the x, 1/2 to the x, 0.9 to the x. How does the graph look different? Adam? Yeah, very good. So if I'm thinking of x, when I get 1/2 to the negative 1, that'll actually be 2 to the positive 1. And it'll start getting bigger the other way. So how would we describe this function in terms of those properties? Decreasing. And then it has the same y-intercept, same asymptote, I believe, right? So some of those things didn't change, but some did. And then, of course, the different transformations will change more of these things.